Okay, so this is part one of the integral test. I keep accidentally going over 13 minutes with this explanation, so I'm splitting it into parts. So let's look at this series. This is just the harmonic series. We talked about how it diverged in the nth term divergence test, and you might be confused because nth term divergence says this approaches zero, so it doesn't necessarily diverge, but integral test will show you why. So let's look at this series, right? It's a function, and we keep changing n by 1. So we have a change in n, and we have this function right here, 1 over n, for inputs of n. So we have a delta n, and we have an f of n, and after multiplying these, we just take the sum of all of them. So this might remind you of something. Yeah, I mean, you can see it up there, but more specifically, if we calculate what this would look like on this graph, this graph is y equals 1 over x. It's just the curve described by this. So, and then these are the discrete values, the actual values we're going to be adding together. But we have a change of 1, and we start at f of n. So we start at 1, change by 1, then go to 1/2, change by 1. Then we go to 1/3, and we change by 1. And we have these rectangles. We now add them together for an infinitely long period of time. You just add an infinite amount of these that are this size, and then we'll get a Riemann sum, an estimate of an integral. What integral are we estimating? Well, we're going to be estimating, obviously, this one from, if we look at this graph, we can call it x. You could also call it n. Miss Young likes calling them x, but you don't necessarily need them to be x. You just need a variable here and the same variable over here. But yeah, so this is the same as, or not necessarily the same, but an estimate of this. Because obviously this is the area underneath this curve from 1 to infinity. Then these are these rectangles from 1 over infinity. So the idea is that if these are estimates of each other, if one of them goes to a finite number, then the other one is also going to be finite. Because, like, if you have an estimate, you could say, yeah, pi is about equal to 3. But you wouldn't say that, like, 15 is about equal to infinity, because it's not an infinite number. It's clearly finite and definite. Even if you said like 1.0 times 10 to the 100, that's still not about infinity. It's a really big number, but if you can prove that this value equals that, you can't say that that's about infinity, because infinity is a lot larger than this. So just the general idea is that if these are estimates of each other, they must do the same thing as they tend towards infinity. I'm not going to show you the work. I would encourage you to do it yourself. But this equals ln of infinity. So it's a divergent integral. So if this one diverges, then this one will also diverge, since they're estimates of each other. For another one, like this one converges to some value, and that value is an estimate of this one. And since this converges to some value, let's call it k, it's just a constant, then we say that, oh, well, this series is about k, and if k is a finite number, we can't say which it is. If you take this integral, I would also encourage you to do it yourself. If you say that, then, well, obviously this will converge. So that's a convergent series. This is also actually the derivation of the p-series tests. I would encourage you to not use the integral test to like do p-series on your actual exam, but just at home right now, I would strongly encourage you to just do these integral tests on like this series. I guess I should probably do them all in one notation. Just like this series, then n squared, and the same thing, but with uh, the square root of n. So you can see just how p-series work. And just prove to yourself that the p-series test makes sense, because there's not going to be a video on this, since it's just derived from the integral test. So that's part one. Part two, we'll be talking about the conditions necessary to check for your series before you do the integral test.